So we will start chapter 11 from today, and it's basically an extension of what we have been doing in the last chapter. So in this case, we now for a given loading condition, we know we have a stress element, and we have stress element, and on that stress element we have different stresses. We can rotate that stress element to a point where we will get maximum principal stresses and maximum shear stresses. Now we have to figure out if that stress state will cause failure or not. So that's what we will do in chapter 11. So chapter 11 is about yield criteria. So we will take that stress element and we will compare it with different yield criteria, and then we'll figure out if the failure will happen or not. So we already know the stress strain curve, right? In chapter 2, we studied about the stress strain curve. So this stress strain curve is actually how the material will behave and what would be the stresses and strains when we keep on pulling the scoop on. So that's how the stress strain curves look like. Also, we'll talk about the Mohr circle. So basically, we were discussing Mohr circle. So right, based on the two-dimensional stress state. But if we have a three-dimensional stress state, this is how the Mohr circles look like. If you have a three-dimensional stress element, this is how it looks like. But we will not go into three-dimensional stress elements. But this is just for you guys that how it looks like. So we can talk about this a little bit. So we already know if we have a stress element, we usually have stresses along x-axis, stresses along y-axis. These are our normal stresses. And we also have shear stresses, right? So we can use this two-dimensional stress element and we can draw a Mohr circle. So this is what we did last time. We can basically draw a Mohr circle and we can represent this stress state on a Mohr circle. So if this is center, so maybe let's just say this, I'm gonna plot this stress element on a Mohr circle. So it would maybe look like this. We don't know, right? So this red line is basically plotting this stress element on the Mohr circle. And by using Mohr circle, we can also extract stress 1 and stress 2. So stress 1 and stress 2 are actually maximum principal stresses. When you will rotate the stress element at a given angle, you're going to get maximum principal stresses. We can also calculate maximum shear stresses, right? So for a given stress element, we can calculate stress 1, stress 2, which are actually maximum principal stresses. We can also calculate tau max, which is the maximum shear stress. And the next step would be to compare with the yield criteria and to figure out if this will cause yielding, will cause failure or not. But just a quick, uh, we can just quickly talk about three dimension, but we're not gonna go into detail. But similar to a two-dimensional stress element, we can also draw a Mohr circle for three-dimensional stress element as well. So in three-dimensional stress element, you will have normal stresses in three dimensions. You will have stress X, you will have stress Y, and you will also have stress Z. You will also have shear stresses along two planes, right? So, so basically, this would be the stresses condition if you have a stress element. And you can rotate the stress element in three dimensions to figure out the maximum stresses, or you can also use equations. So if I want to draw the Mohr circle for a 3D case, so this is how we can draw the Mohr circle. So for example, you can calculate stress 1, you can calculate stress 2, you can calculate stress 3. That's going to be the maximum stresses uh, which you will get by rotating the stress element at an angle theta b. So the procedure is similar. Before we had stress 1 and stress 2, right? Like before, we could have drawn a circle by calculating the center and calculating the radius. We can also do this with stress 2 and stress 3, and we can also do with stress 1 and stress 3. So just the process is similar, but in 3 dimensions you will have 3 circles. But we are not going to go in detail. But if you see something like this, so you can just understand that it's the same process, but this Mohr circle is for a 3 dimensional case. So let's talk about yield criteria today. So this is chapter 11. This chapter 11 is about yield criteria, right? So remember in chapter 2, we were talking about stress strain curves. So if you take a test specimen, a coupon, and if you put it in a machine, this is what we were talking about in chapter 2. And if you keep on applying a uniaxial load, you will observe a stress strain curve, right? So I'm just gonna quickly go through this because we did this in chapter 2. So you put a coupon, a test specimen, you try to keep on applying the loads and you will observe the stress strain curve. So this is what the stress strain curve looked like, right? This was stress, this is strain. So this is what we will get if we test any material. And this we will get for ductile materials. So this stress strain curve is for ductile materials. And you have another type of material which are called brittle materials. And if you try to draw the stress strain curve for brittle material, you will get something like this. So in a ductile material, you will have yielding, you will see yielding at this point, and you will observe a lot of plastic deformation. You will observe strain hardening, and then you will observe necking, and then you will observe fracture here. So that's fracture. But when we talk about brittle materials, you will observe yielding somewhere here, which is not predefined usually. And right after yielding, you will observe fracture. So we can extract all this information from any material. All we have to do is that extract a coupon of that material, put that material in a UTM machine, and apply a uniaxial load. And if you apply a uniaxial load, you can observe for any particular material what will happen when you apply that load. So if you apply that load, you can calculate the stresses, and you can observe for a given material. If it's a ductile material, you can calculate this stress value, and this stress value is basically, I'm going to represent it at y, but this is y is that given stress where the material will start yielding in this loading condition. Like when you have a uniaxial loading condition, then the material will yield at this stress level. And if it's a brittle material, it will yield at this point. So we for all the materials, we already know what the yield stress is. So if you extract a given material, put it in a machine, and you do this uniaxial loading test, you will know when yielding will happen. So we know this. But what happens if this material is not loaded in uniaxial stress, but it's loaded in different way? For example, in most of the cases, for example, if we have a beam, it's loaded, you have uniformly distributed load, you have moment, you have torsion. So this is a different stress state than this. So we don't know when yielding will happen in this case. We don't know. But if we just take a sample out of it and we test it in a machine, so we know for this loading condition, the uniaxial loading condition, we know when the failure will happen. But in actual scenarios, you don't have a uniaxial loading condition. You have different loading conditions. So now we have to figure out when the material will fail. So it's a little more complicated than just using uniaxial testing in a machine and see the yield here. So we have to figure out when the material will yield in this situation. So in this situation, we already know when the material will yield. But we have to figure out when the material will yield in this situation. And yielding means failure for our case because we don't want material to go beyond the stresses of yielding, because after yielding you will have permanent deformation, and for the brittle material it's even riskier because you can have fracture. So this is what we have to figure out. So there are different theories which come up with solutions where if we know this yielding, then we can try to figure out yielding in this case as well. So they have different theories for ductile materials, and they have different theories for brittle material. So if you have a ductile material, we want to know in this case when the material will yield, right? So all we can do is like we can extract a stress element out of this loading condition, which we will see how we can do in one chapter which is remaining. So this is the stress element. We can take stress element out. We know the stress element have different loads, and then we're going to perform everything what we were doing in Mohr circle, and we'll calculate stress 1, we'll calculate stress 2, and we'll calculate tau max. And we can calculate these stresses using Mohr circle, using transformation equations, using equations for the maximum principal stresses. And these are the maximum stresses which we will get. We will not get more stresses than this. In given loading condition, we can extract the stress element and we can calculate the maximum stresses we will observe given this loading condition. Now there are some criteria which different researchers have come up with, which compare this with the yielding and to figure out if the yielding will happen or not, if this configuration will observe yielding or not. So there are different methods to do this. For ductile material, you have two theories which can try to predict yielding when you have a complicated loading condition. One is called Tresca theory, and another one is called von Mises theory. And for brittle material, the theory which we're going to use to predict failure is called Coulomb's theory. So you understand why we are doing this, right? Because for a uniaxial loading condition, yielding, we know when yielding will happen, right? But we don't know if you have a combined loading case, if you have a different loading scenario, we want to figure out that when failure or yielding will happen in our case, because that's the real world situation where you have a beam or column or some other structure system where you have loading condition. So these theories, we're going to make use of this information and we'll try to predict yielding or failure. So we're going to talk about Tresca and von Mises if a material is ductile. If the material is brittle, then we're going to use Coulomb theory for our purposes. So these are the three theories which we're going to talk about. So let's talk about the first one, which is Tresca. So this is for ductile materials. For ductile materials, we're going to use Tresca. So Tresca theory is also called maximum shear stress yield criteria, because it says that we will observe yielding. So yielding will occur, yielding or failure. Yielding occurs when this stress xy absolute maximum, this is just, is equal to y by 2. So this theory says if our stress, this stress we will calculate from the stress element, is equal to half of the yielding which we will get from the uniaxial testing machine, then you will observe yielding. And they did some experiments also, and it follows the experimental verification. So yielding actually does happen for a complicated case. When we take out the stress element, we'll calculate stress 1, stress 2, tau max. We'll use the equation to calculate this stress. And if we compare it with half of the yielding, then the yielding start happening. So that's the Kreska theory, which says, and this we can calculate using, so this is basically uh, subtraction of stress 1 and stress 2 and divide by 2, so which is also the maximum shear stress. So I'm just gonna write this, how we can calculate this stress x y absolute. So we can calculate this by using this equation, which is maximum of stress 1 minus stress 2 by 2, stress 2 minus stress 3 by 2, and stress 3 minus stress 1 by 2. These stresses we can extract from a stress element, right? So we can calculate this, and this is the material property, so we can figure out if the failure will happen or not. We can also simplify this by extracting a yield criteria. So maybe all you have to remember is this yield criteria. So for this theory, all you have to remember is this yield criteria. So I'm going to write it down. This is coming from these two because this stress is stress 1 minus stress 2 by 2. This is by 2. So basically we are canceling out this, and that's what's remaining. So I'm just going to write down the yield criteria, which is stress 1 minus stress 2 greater than equal to yield, right? And if you have a three-dimensional stress element, then you also have stress 3 So we'll have two more equations. Stress 3 minus stress 1 is, so even if you don't understand this, all you have to remember is these three equations. So if you can calculate stress 1, stress 2, and stress 3 would be 0 for a two-dimensional stress element, but for three-dimensional stress element, you will have some value for stress 3. So once we have this, you can basically check these values with the yield criteria, and if these values are higher than the yield criteria, then we will conclude that we will observe yielding, and it's like a failure of a system. So which we don't want. So if this happens, uh, you will observe failure. So all you have to remember is these three equations. So that's Tresca theory. So Tresca theory says calculate the maximum principal stresses, subtract them, and see if the combined stress you're getting from the stress element is higher than the yield stress or not. If it's higher, then it's a failure. Then we will observe yielding in a given stress environment. So that's which is called Tresca theory. Now the another one is von Mises. So von Mises was another guy who tried to predict failure in a given loading condition, but through a different way. So he used strain energy instead of maximum stresses to calculate the yielding or failure of a given loading condition. So another one is von Mises theory. It's also called maximum strain energy yield criteria. And this is the most famous one. All the finite element analysis tools also use this theory to calculate the yielding. So if you have seen any finite element figures, they use von Mises to calculate failure. So von Mises says yielding occurs when your stress Vm is greater than or equal to yielding. So what he did, instead of using stresses, he actually calculated the strain energy between the materials when it's stressed, and he figured out that strain energy can also be used to see if the material will yield or not. But the strain energy, the stresses you're getting from strain energy, if they're higher than the yielding of uniaxial testing, then you will observe yielding, otherwise you will not observe yielding. But this stress from the strain energy can also be calculated by using stress 1 and stress 2 by one formula, which I'm going to give it. I'm going to write it down here. So all you have to remember is this yield criteria. Which is stress 1 minus stress 2 whole square plus stress 2 minus stress 3 whole square plus stress 3 minus stress 1 whole square divided by 2. So if it's a two-dimensional stress element, stress 3 would be 0, but otherwise this strain energy can be represented with this equation, and we can calculate all these values from stress element, from Mohr circle, from principal stress equation or transformation equations, and we can compare it with the yielding, and we can figure out if the failure will happen or not. So that's for the ductile materials. And there is one, if the material is brittle, then we cannot use these two theories because they're not going to give us the right answers, because if you they also did experimental verifications, so these two theories are very good to predict yielding for a ductile material, but if the material is brittle, so they don't give the right answer. They're just, so we have to use other theories. So for brittle material, we're going to use different theories, and one of the theory which people usually use is called Coulomb's theory. And it's also called maximum normal stress yield criteria. And it's actually pretty straightforward. So I'm gonna write the yield criteria, which you guys have to remember. So the yield criteria is you have to take stresses, original stresses, stress 1, which is the maximum principal stress, and if it's more than the yielding material, then it will fail or yield. And similarly, you can also compare other principal stresses, and if it's a three-dimensional stress element, you can also compare it with sigma 3. So we can calculate this stress 1, stress 2, and if you have a three-dimensional stress element, stress 3, from the stress element, and we have to compare it with the yielding of material under uniaxial testing, and if the stress is higher than the yield, then we will observe yielding. So that's what Coulomb's theory says, which is, pretty intuitive, because these are the maximum stresses which you're going to get in a given loading state, and you just have to compare these maximum stresses with the yielding. And if it's the maximum stresses are higher than the yielding, then we'll observe failure or yielding. So that's all there is. And we can just do one example. And once we'll do it, one example is gonna get super clear because it's just an extension of Mohr circle and extension of transformation equations. So the first step is to calculate stress one, stress two, and once we have those, we can just use these yield criteria to figure out if the material or under given loading condition will observe yielding or will fail or not. So we can do example 11.1. So the first few parts are same. So it says you have to draw Mohr circle. So you guys can try to draw Mohr circle. And you also have to calculate the principal stresses, which you guys can calculate an angle of rotation. The third part is draw stress element, which you can do. And then the last part would be to see if that particular stress element will fail under these loading condition or not. So this is our example. So the only difference is this time they have given us the material. So the material is A36, which every material has a specific yield stress. So in this case, the yield stress is 250 megapascal. So this is the A36 material. So I can give you two information. So in exam also I will provide you the yield stress. I will also give you if this material is a ductile material or is a brittle material. So this material is ductile material. So this information we got from a coupon test. So we make a sample out of this material, we put it in a testing machine, we extract the stress in curve by applying uniaxial load, and this is the information which we get from the material testing. So we know this material under uniaxial loading condition is going to have yielding at 250 megapascal. So under uniaxial loading condition, when the stress will reach 250 megapascal, we'll observe yielding in that specific. And we also know it's a ductile material because we observe this kind of stress strain curve for this material. But at this loading condition, we don't know that if this will have this in this loading condition, we will not see yielding happening at 250 megapascal. We will see yielding happening at some other stress, and this is what we have to calculate, and this is why we're using different failure theories. So we have the stress element. We're gonna draw Mohr circle. We can also use transformation equations. We will try to calculate stress 1, stress 2, tau max. We'll calculate all those values. But for our purposes, we only need stress 1 and stress 2. So once we have those stresses, these are the maximum stresses which we're gonna get for this stress element. And we will use different yield criteria to compare our stresses, stress 1 and stress 2, with the yielding to figure out if the material will fail or not. So the first step is draw Mohr circle. So you guys can try to draw Mohr circle using this. So you have to calculate center, you have to calculate radius, and you have to draw the Mohr circle. So you guys can start drawing the Mohr circle. So first step is draw Mohr circle. So we can just draw Mohr circle. So in order to draw Mohr circle, we need two things, right? We need center and we need radius. So if you know center and radius, you can basically draw a Mohr circle. So in this case, you guys can assume one box equal to maybe 10 megapascal. And you can try to draw Mohr circle in this case. we can also plot this stress element on a Mohr circle. So if you do this, I think you're gonna roughly get something like this. Oops. I'm just roughly doing because everybody knows how to draw Mohr circle. So you guys can comfortably draw the Mohr circle. So it would look something like this. This is our stress 1, this is our stress 2, this is tau max. You could also calculate the angle of rotation, theta p, which is this. And you could also calculate theta s, which is 2 theta s, which is this angle. And this angle is 90 degrees. So that's the first part. The second part is determine principal stresses and angle of rotation. So you can calculate principal stresses. This is more important because principal stresses are gonna be utilized in the yield criteria. So that's A part. The B part is you have to calculate principal stresses, which is stress 1 and stress 2. And you also have to calculate theta P in this case. From Mohr circle also you can extract this information, stress 1 and stress 2. You can also use transformation equations. You can also use the formula for maximum principal stresses, and you can calculate stress 1 and stress 2. And if you do this, you're gonna get stress 1 as 146 megapascals, and you're gonna get stress 2 as negative 126 megapascals. And if you want to draw the stress element, this is anti-clockwise to theta p, so it's some stress element. If you rotate the stress element at theta p, you're gonna get maximum normal stresses, which are also called in-plane principal stresses for a two-dimensional stress element. So you will have this force, which is stress 1, which is going to be 146 megapascals, and you will have stress 2, which is negative, so compressive, and it's gonna be 126 megapascals. So under our loading condition, we have extracted a stress element, and the maximum principal stresses which we are getting in our case for our loading condition is 146 megapascals and 126 megapascals. So these are the maximum principal stresses which we're going to get. So you can see the yielding is the yield. This material, this given material will yield at 250 megapascals, right? But the maximum stresses which we are getting is 146 megapascals. So that's the maximum stress which we get. And it's a ductile material, so now we have to use those yield criteria to figure out that under our condition, our loading condition, will this material or the loading condition will fail or not. So we will use, first we have to figure out if it's a ductile material or a brittle material. So we know it's a ductile material, right? So for a ductile material, you have two theories. You have Tresca, and you have von Mises. And we're going to use both of these, and we will see if in our case we will observe yielding or not. So let's talk about Tresca failure theory. So it says yielding will happen. So I'm gonna write down the yield criteria for Tresca theory. So I'm gonna write down yield criteria. So yield criteria is stress 1 minus stress 2. If it's more than yield, then we're gonna observe failure. And we also have two more equations, stress 2 minus stress 3. If it's more than yield, we'll observe failure. And stress 3 minus stress 1, if this is more than the yield of material under uniaxial testing, then we will observe failure. So from Mohr's circle, we have already calculated stress 1, and we have already calculated stress 2, we have already calculated stress 3. So we can use this yield criteria to see if we will observe failure or yielding in our case or not. So our stress 1 was 146 megapascals. Our stress 2 was negative 126 megapascals. And stress 3, because it's a two-dimensional stress element, so stress 3 is 0. So if you use this, our stress 1 is 146 minus our stress 2 is minus 126. Should be greater than equal to, our yield is 250, right? So if you solve this, you're gonna get 272 megapascals, which is greater than equal to 250 megapascals. You can do for this also and this also, but we can see that 272, our stress, our combined stress, this maximum shear stress is higher than the yield. So this theory says that it will yield because our stress is higher than the yield. So this is true, right? This condition is true. Therefore, it will yield and failure occurs. So if we use Tresca failure theory under our loading condition, this theory says that it will fail. So you will observe yielding in our given loading condition. So either we have to reduce the load or increase, use different material or increase the cross sections, do something about it, because under these given loading condition, we will observe yielding and we will observe permanent deformation, which is not what we want. So now we can also use von Mises to figure out if we will observe failure or not. So von Mises theory. We're going to use von Mises theory now. So I'm going to write down the yield criteria for von Mises. So von Mises says that if our stress, von Mises stress, is greater than or equal to yield. If this is true, then we will observe failure. And this sigma Vm, we also have a formula for this, which is stress 1 minus stress 2 whole square plus stress 2 minus stress 3 whole square plus stress 3 minus stress 1 whole square divided by 2 should be greater than or equal to yield. And we know these values. Stress 1 we know is 146 megapascals. Stress 2 we know is negative 126 megapascals. And stress 3 we know is 0. So you can use these stresses, and these stresses are those stresses which our stress element is experiencing. And this Y is that stress which under uniaxial stress state you will observe yielding. So if you use these equations, you can try to figure out if our stresses because of the von Mises are higher than the yield stress or not. So if you solve this, you guys can try to solve this and let me know what values you are getting. But if you try to solve this, I am getting 230.46 megapascals, which is greater than equal to 250 megapascals. So in this case, this is not true, right? Our stresses get what we are getting from strain energy from von Mises stresses. So this is our stress state. These are the stresses in our stress element, which are not higher than 250 megapascals. So this is not true. This is not true. So it will not yield. We will observe no failure. No failure occurs. So that's how we figure out if the material will fail or not fail. And by failure, I mean if it will yield or not yield. And if it's not yielding, then it's safe. So to back up a little bit, we can calculate the yielding for any material, right? So all we have to do is that we take a coupon out of a material. So for example, if you want to test steel, right? So we take one sample of steel and we put it in a machine and we apply a uniaxial loading condition, right? So we apply a uniaxial load and we can calculate yield stress. So under this loading condition, we know when yielding will happen. But actual scenarios are different. For example, if you are designing a building, right? So if you have a building, so you have wind loads, you have snow loads, right? You have all sort of loads, and if so, you have to design all those components for building or a machine. So let's say we are talking about this component. So we're gonna take this component out. So this is maybe a simply supported beam. This one component, maybe a simply supported beam. So in this simply supported beam, you have different loadings, right? You have people are walking on this beam, so you will have like dead load because of this, live load, and all these kind of different loadings. So this is a little bit complicated than the thing we know. So we know a material when the material will yield, but in actual loading condition, we don't know. So what we do is that we calculate shear force, bending moment diagrams, all these kind of things. We extract that stress element. Maybe we know if this is the maximum bending moment value. We're gonna extract the stress element, and we can also calculate. We can also determine all those stresses. We will learn this in next chapter. So once we have this stress state, we can figure out the maximum stresses, and we can compare this with the thing we know, and then we can figure out if the failure will happen or not. using the failure theories which we discussed today. So that's like overall how we design or analyze different machines, buildings, structures to see if it will fail or not.